Alright, let's continue with, we looked at one tail and two tail test. Now, uh, before we go back at focusing on two tail test, let's look at a situation using um, the absolute value function. So in the following example, we have a standardized or a standard normal random variable, and we want to find that probability. So it's a absolute value, and what we do is we know we can remove the absolute value by using its hybrid function. Okay, so you come up with those two values, and as you make z the subject, you end up with two different inequality. Because the standard normal distribution is symmetric about 0, as those two values are equal, we can substitute and we get the double of either probability, and we end up with this value. So in order to apply that symmetry of the normal distribution to determine the probability, the first thing you need to do, because we dealt with z, it means we need to standardize any x random variable. So here we have that example. It's an x random variable. It's a normal distribution. We have the mean and the standard deviation. Find the probability that a single value of x is at least 2 units from the mean. So we're going back to the definition of what it is. So it is that difference as a modulus, it has to be greater or equal to 2. Then we rearrange it and we get 2 over 5. So that difference over the standard deviation. Now that amount on the left has been standardized, so we substituted that value, and from that modulus, from the previous example, we can make it equal as the double of that probability without the modulus, and so on, and we get the final numerical answer. So really remember to use that formula and just transfer it or turn it into a standardized form for the probability. Okay, so what we do, if you want to reject the null hypothesis, we want that distance between the observed sample mean and the hypothesized population mean, and it needs to be more than explained by the normal sampling variability. So what we do is, if x is the random variable as the sample mean, and it represents the mean of the sample of size n, then we can write that distance that way. Hold on. Alright, so now we have defined that. So that's the sampling variability, and over there will be the distance between the sample mean and the population mean. As we rearrange that as a standardized form with a modulus, we get this probability, and that will give us our p-value. So let's look at an example. Just pause the video, read the situation, write down the preconditions, and read the questions as well. Alright, so we have our x variable. It's a normal distribution, has a mean of 50 kilograms and a standard deviation of 1.5 kilogram. We have a random sample, the size is 10. Now find the probability that the mean weight of 10 bags in the sample differs by 1 kilo or more from the population mean of 50 kilograms. With that, we applied straight away the formula. On the right hand side, we will have our hang on. Alright, yes, we have a distance has to be greater than 1. we divide by the sample standard deviation. We'll get, so that sigma over root n is the 1.5 over root 10, and the left hand side is your standard normal variable. Therefore, we can simplify that without the absolute value, and we get that answer. That answer is from the CAS. We use inverse normal, and we get 3.5%. So now we're in a situation where our mean of the sample is 49.1. So we're gonna, right hand side will be that 49, that distance will be 49.1 minus the mean divided by the the sample, the standard deviation of the sample. So we get the standardized variable on the right hand side. We get rid of the modulus and we get 5.78%. So we know our alpha is 5%. As that p-value is greater than 5%, we have insufficient evidence to conclude that the mean weight of the bag of sand is not 50 kilograms. So there's not a strong evidence to move away from the 50 kilograms. And that's it for 16C, and I'll see you in the next and last video.